Okay, I'm going to talk about energy and chemical reactions. So first off, if you want to talk about energy and chemical reactions, you probably need to know something about some energy units. Now in chemistry, probably the most common energy unit we use is joules, and the abbreviation for joules is J, a capital J. Um, and it is the SI unit of energy, meaning that's kind of the standard in science. And if you have an equation that calculates energy or uses energy in the calculation, usually it needs to be plugged in joules or it's going to come out in joules. Um, Now, joules is what we would call a combined unit, meaning it's made up of other units. So as you can see here, a joule is a kilogram times meters squared per second squared. Um, but most of the time we would just write it as joules. The only reason that would be important is if you're trying to relate an energy to like masses or velocities, things like that. Um, I give you a couple other relationships there that a joule's a Newton meter. That's more applicable really to physics type concepts, so we won't use that. Um, and then I've got a kilojoule equals 10 to the third joules there. That's just a basic metric conversion. So really, joules, you can tack on any metric prefix you want, and it's going to have the same type of relationship as other units that you would tack on metric prefixes. Another thing that you can relate joules to is liters times atmospheres. That comes up usually when you're dealing with gas samples, which we're not going to do at the moment. So that's just an additional conversion that sometimes it's useful to be aware of, but not necessarily memorize it. Okay. Now, we could also have energy in units of calories. That's another common one in chemistry. Now, in chemistry, when we say calories, the, the abbreviation is CAL with a lowercase c. Okay, that's what we're talking about in chemistry when we talk about calories. Um, and that's the amount of heat necessary to raise the temperature of 1 gram of water by 1 degree C. So this is a unit that is based off of water and the behavior of water. And you can relate calories to joules. A calorie is 4.184 joules. You can also use metric prefixes with calories. So a kilocalorie would be 10 to the third calories. Now that actually ties us to what they talk about in biology or in like a nutrition type class when they talk about calories. Or if you look at your food labels and you see calories, that's calories with a capital C. Okay, so the abbreviation is capital C and lowercase al, okay, instead of all lowercase. So a true calorie in chemistry is all lowercase for that abbreviation. But when you see calories abbreviated with a capital C, that is talking about calories in terms of kilocalories. Okay, so a capital C really is a different way to write kilocalories. I guess because kilocalories maybe would sound scary to people. And so when it's on food labels on the scale of kilocalories, they don't want to put it as kilocalories. And so they just change the unit abbreviation to call it still calories. Okay, but in chemistry, we're mainly going to deal with joules. And if we deal with calories, we will usually deal with the standard calorie. Okay, now another thing that you need to be familiar with when you're dealing with energy is the law of conservation of energy. Okay, and it's just like the law of conservation of mass. The law of conservation of mass tells us that mass cannot be created or destroyed. Well, the law of conservation of energy tells us the same thing, but about energy. Okay, so energy cannot be created or destroyed. What we can do with energy is we can convert it from one form to another. Okay? So when it seems like maybe energy is being produced by something or energy is being consumed by something, it's generally being transformed from one type to another. So it seemingly appears or it seemingly disappears, although it doesn't really. Okay. And so a lot of times when you're dealing with energy, you're dealing with interconversions between kinetic and potential energy. That's the most common that you're dealing with. Now, you can break that down into more categories, or we can be more specific. So in chemistry, most of the time, the type of kinetic energy we're dealing with is thermal. Okay? And so it's the heat that is associated with these substances or reactions, whatever you're dealing with. Whereas the potential energy is what we would call chemical energy. And so that has to do with the arrangement of the atoms within a molecule, or how it's bonded, how all of those atoms are interacting, is associated with that chemical energy. Okay, and so usually in chemistry, we're looking at interconversions between thermal and chemical energy. Now, that energy can also be transferred, or energy can be transferred in different ways. So we can convert it from one form to another, and it can just be transferred from one thing to another as either heat or work. Okay, and we'll focus on heat. Usually you only deal with work energy when you're dealing with gas samples in chemistry. Most of the time when we're looking at the transfer of energy in chemistry, we're focused on the heat being transferred. And so that you would see if there's like changes in temperature, then that's because there is some heat being transferred. Or if you have phase changes of substances, that would indicate that there's some heat being transferred. Now, work generally is associated with some sort of motion, okay? And a lot of times in chemistry, we're just kind of mixing things and then a reaction's happening. There isn't really, the reaction isn't causing something to move. In general. Now, when you're dealing with gases, you can deal with gases expanding, or you can compress a gas, and that's all associated with work. But we will focus on heat. And so if we're talking about a reaction, so some sort of chemical reaction, you can have either heat being absorbed or heat being released by that reaction. Okay, and we have terminology that relates to that. And that terminology is endothermic and exothermic. So if we classify a reaction as an endothermic reaction, that's a reaction that is absorbing heat, okay? And that heat is energy. So it's absorbing energy in the form of heat, okay? And so that means that your reactants are starting at a lower energy and your products actually end up with a higher amount of energy if that is absorbing heat in the process of that reaction. Okay. On the other hand, you can have some reactions that actually release heat as they convert reactants to products. And if that's the case, then the reactants have a higher energy than what the products do, because some of that energy is leaving the system in the form of heat. Okay, so you should be familiar with those terms, endothermic and exothermic, with respect to what that means for a reaction. And it basically is just telling you, is heat leaving the reaction or is it coming in, which is then going to tie to the energy of the reactants and the products. It's going to tell you something about how they relate to one another. Okay, now, if you actually want to quantify the heat change in a chemical reaction, so how much heat is released or absorbed by a reaction, you can do that numerically. Now, very often, if it is quantified for a reaction, they typically would quantify it in terms of an energy per amount of either a reacting substance or a substance that's being produced. And so it's kind of scaled on a, per amount basis. That way, that information can be applied to any amount of stuff that you want to react or any amount of stuff that you want to produce. So sometimes you'll see these heat values written off to the right side of a chemical reaction. A lot of times they're labeled as delta H. So you might have a chemical reaction and next to it a delta H value, and that's telling you how much heat is either released or absorbed by that reaction, and that is scaled to that reaction. So if it's written next to the reaction, it's talking about if 1 mole of the reaction occurs, which then you can relate to each substance in the reaction. So you can do that, and that's typically for just any reaction that isn't of some special class. But there's a lot of reactions that you have, kind of the same thing happening, like combustion reactions. You can look up heats associated with combustion reactions, and they generally don't tell you the reaction because they assume combustion means something's reacting with oxygen and forming usually CO2 and H2O. And so sometimes it's given with a reaction, sometimes it's just given and you're told it's based on a certain substance in that reaction. But it's always going to be some energy per amount that's given. And so that energy per amount could be in terms of a per mass, or it could be per moles, okay? So those values will typically have units like kilojoules per gram or kilojoules per mole. So then you can apply that to your particular scenario. If you're performing the same reaction, but you're not using a gram, or you're not using 1 mole, you're using some other amount, then all you have to do is you take that value and you multiply it by the number of grams or the number of moles to get the actual heat associated with your reaction, okay? So you're given a standard kind of for this particular reaction. This is how much heat is released or absorbed for a given amount of stuff that is reacted, okay? And then if you multiply by the specific amount that you react, then you get the actual heat. So let's look at a couple of those calculations. So here I've got the heat of combustion of iron is negative 412.1 kilojoules per mole. And it says how much heat is released when 0.250 moles of iron is combusted. Okay, so we have a combustion of iron. That means iron's reacting with oxygen, and in that case, a metal reacting with oxygen, it's going to form a metal oxide, so some iron oxide. And in that process, it tells you the heat of combustion is negative 412.1 kilojoules per mole. And I want to point out that negative, all that means is that heat is released. Okay, so in chemistry, when we're dealing with energies, sometimes we'll put positive or negative signs with it, and that's just telling you where the energy is going. Okay, so if it's positive, that energy is being absorbed. If it's negative, that energy is being released. So in this case, when iron is combusted, it releases energy, specifically 412.1 kilojoules per mole. Okay, and we want to know how much heat is released when 0.250 moles of iron is combusted. So all we need to do really is multiply those numbers. So we have the negative 412.1 kilojoules per mole, and that's really per mole of iron, right? And so then if I multiply by 0.250 moles iron, Okay, my moles of iron are going to cancel, and I'm going to get the amount of heat released. So I have the negative 412.1 times 0.250, and let's see, based on my moles, I'm going to round to 3 sig figs, so I'd get 103 kilojoules. Okay, and yeah, it comes out negative. And you can either say it's 103 kilojoules are released, or you could say it's negative 103 kilojoules. The negative indicates it's being released. Okay, let's do another one. So this one is a little bit trickier. So here we say we have the decomposition of aluminum chloride, and it absorbs 704.2 kilojoules of heat per mole of aluminum chloride. So let's write that down, 704.2 kilojoules of heat per mole of aluminum chloride. So that's AlCl3. That's an ionic compound. If you know the charges, you can get the formula. That. There we go. Okay, so let's see. Then it says how much heat is absorbed when 10 grams of aluminum chloride decomposes. So we have 10 grams of aluminum chloride. Now this one I can't just multiply. If I just multiply these two, I'm going to get kilojoules times grams divided by moles, which is senseless. It does not, that's not a quantity of heat. Okay, so you need to get it to where your units cancel. So the heat for the reaction is given in kilojoules per mole. So really it would be best to first convert your grams to moles. Okay, you could convert your heat from kilojoules per mole to kilojoules per gram, but that generally is more confusing for people. So we will convert our 10 grams of aluminum chloride to moles first. So I'm going to put grams of aluminum chloride on bottom. So I'm just always setting things up as dimensional analysis, setting it up to where I can watch my units and see them cancel. Okay, so for this, let's see, we would have had we have 26.98 for aluminum plus 3 times 35.45 for our chlorine, and that gives us a molar mass of 133.33 grams per 1 mole. So that cancels my grams of aluminum chloride. Now you can stop and calculate, or that you can continue the dimensional analysis, which is what I'll do. Because now I want to get rid of moles of aluminum chloride, and I want to go to kilojoules. Okay, so I want to get the heat. And so it's 704.2 for 1 mole. So the moles cancel, and that's going to give me my heat. So here I've got 10 divided by 133.33 times 704.2. And based on my 10 grams, I'm going to round to 3 sig figs. So 52.8 kilojoules is how much heat is absorbed when I decompose 10 grams of aluminum. Okay. So you should be able to quantify the heat associated with a specific reaction based on known information about that reaction. Okay, so a heat per gram or a heat per mole piece of information.